part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss Faraday's law and the Flux Rule. I'll begin this lecture with a discussion of 3 experimental observations made by Michael Faraday back in the 1830s. The first of which is if you have a conducting loop in the presence of a magnetic field, and you pull that conducting loop through that magnetic field, you'll see an EMF induced in the loop. Second experimental observation, if instead you hold the conducting loop stationary, but move the magnet in the presence of the loop, once again you'll see an EMF induced in the loop. Third observation, if you hold both the magnetic field or the source of the magnetic field stationary and you also hold the coil stationary, but increase or decrease the strength of the magnetic field, what you'll also see is an EMF induced. So in all 3 cases, you have an EMF induced in the loop. And this, all 3 of these can be described by this one expression. The EMF is equal to minus the time derivative of the magnetic flux, and the flux, as you'll recall, is defined as the surface integral of the magnetic field dotted into the normal of the surface over which you are integrating. If you were to take calculate this integral over a closed surface, this will vanish, and that of course is the consequence of the divergence-free nature of the magnetic field. So this is really a remarkable result here. In the first case, if you've got a conducting loop that I'm moving, or somebody's doing mechanical work, this is really the Lenz force law. And the EMF in this case is magnetic. Well, the latter 2 experiments, the loop is stationary. Magnetic field seen by the loop is changing. So this is a different mechanism at work here. So basically, you have a changing magnetic field that induces an electric field. We got two different mechanisms in play here. First case, we've got the Lenz force law, and the EMF is magnetic in nature. Second case, we've got the changing magnetic field induces an electric field. So this is a remarkable thing. We've got 2 different mechanisms here. And these 2 different mechanisms are contained within this one principle. Okay? In this first case, we're really talking about motional EMF. In the other case, the magnetic field's changing, so I'm going to go ahead and start from our Flux Rule. And from the previous lecture, the EMF is equal to the line integral of the electric field around a closed circuit. Now, of course, if we were in electrostatics, this integral would automatically vanish because electrostatic fields are conservative. Not so when we get into time-varying situations, okay? So, anyway, for the case we're looking at, we've got time-varying fields at play, so therefore, the line integral of this electric field, not electrostatic, definitely not conservative, is equal to, on the right-hand side, minus surface integral partial derivative of the magnetic field with respect to time dotted into the normal to the surface over which you are integrating. Okay. By use of Stokes' theorem, I can convert this line integral into a surface integral. And since this must hold for arbitrary surfaces, the integrands have to be equal to each other, and I wind up with Faraday's law in differential form. Okay? So this is a flux rule. And this is Faraday's law. I will point out to you that a lot of folks out there call this Faraday's law as well. So there's another school of thought and reserves the term Faraday's law for this expression and calls this the flux rule. So I will follow this second school of thought. When you have the curl of the electric field is equal to minus the time derivative of the magnetic field, that's Faraday's law, and the EMF is equal to minus the time derivative of the flux is the flux rule. Okay? And the reason why I'm going to draw that distinction there is because there are two different mechanisms contained in this one principle. So that's a remarkable thing. A couple of points that I want to make before we move on is that these observations are basically what led to the development of the theory of relativity. I won't delve into that further. That's a lecture for another time. Another point I want to make, and it's far less well known, is that Faraday's law, Faraday's induction, can be understood in terms of the acceleration of charges and not just in terms of field theory as we're developing it here. So just FYI, I may do a lecture on that at some point. That's for the future when you talk about the linear-Wiegert potentials. There's a way of understanding these rules in that context, okay? Let me just say a few words about the sign here. Basically what that's telling you is that if the magnetic flux changes, magnetic flux changes, that which happens opposes the change. So in other words, we're saying that as nature resists change. That opposition to the change is incomplete, it's only partial. But this is a useful rule for helping you determine the signs. It's really a consequence of Faraday's law. It also holds for motional EMFs as well. That's Lenz's law. Okay, so what I'm going to do now is I'm going to show you a few simulations because I think that's a better way of explaining how Lenz's law works. So we'll go over to that right now. Let's suppose a uniform magnetic field exists in a region of space. A conducting circular ring is situated perpendicular to the constant magnetic field. The flux through the ring is just pi r squared b, where r is the radius of the ring. No EMF is induced because the field remains constant and the loop is stationary. Now let's suppose the magnetic field increases as a function of time. An EMF will be induced such as to oppose the increasing magnetic flux. The induced current flows in the clockwise direction as viewed from above, and the counterclockwise direction as viewed from below. This induced current gives rise to a magnetic field that points in the opposite direction of the increasing magnetic field. Change is opposed, but this opposition is not complete. Now let's suppose the magnetic field decreases as a function of time. An EMF is once again induced, but in the opposite direction. The current flows in the counterclockwise direction as viewed from above, and clockwise from below. The induced current gives rise to a magnetic field that points in the same direction as the decreasing magnetic field. Once again, change is opposed. Let's next consider a system where the magnetic field is not uniform. A long straight wire carries a steady current I. Next to the long straight wire is a circular loop. The colored circles represent magnetic field lines, with green representing the highest magnetic field depicted and pink representing the lowest magnitude of magnetic field depicted. The direction of the magnetic field lines can be determined from the right-hand rule. Thumb points in the direction of the current, and your fingers curl around in the direction of the magnetic field. There is magnetic flux through this loop, but since the flux isn't changing, no EMF is induced. In this next case, we see the loop being pulled to the right. Since the magnetic flux through the loop decreases as the loop moves further away from the long straight wire, an EMF is induced which tends to oppose this change. Let's consider this one more time. Notice that the induced current flows in a clockwise direction from this point of view, and that the induced magnetic field points in the same direction as the magnetic field lines due to the wire. Notice that we're pulling the loop parallel to the wire this time. The magnetic flux through the loop doesn't change, so no EMF is induced. Now that we've looked at a few simulations involving Lenz's law, let's look at some motional EMF examples where we actually calculate the EMF to certain kinds of systems. Let's first consider a rod or bar that's moving in a magnetic field. Magnetic field is uniform and points into the board. I'm going to pull bar to the right with velocity v. So there'll be a magnetic force on the charges. And that is equal to Q times the cross product of the velocity and the magnetic field. So what happens here, if we take v to the right, so it'll be in the x direction, cross that into minus b in the z direction, so we have basically a minus sign from the cross product of the two unit vectors and another minus sign, so we'll just give qvb y or upwards. So there'll be a magnetic force driving charges upwards, and there'll be a charge separation. So as time goes by, and this won't take very long, because of the charge separation, you're going to have an electric field set up as well, and that electric field is equal to QE, and that will be downwards. At some point, this electric force downwards is going to counteract the magnetic force upwards, and therefore at some point when the electric field magnitude is equal to the speed times b, you will have reached an equilibrium. because there's an electric field between the top and the bottom part of the rod, that means there's a potential difference. And we'll call that VAB. And that's equal to E times the length of the rod, which we will call L. And that's equal to VBL. So it's not the magnetic force that's doing the work on the charges. I'm pulling the rod to the right with velocity V, so I'm the mechanism that's doing the work on this system. Now let's suppose that we place this rod on a U-shaped conductor, so I make it free to slide, but I'm still going to be pulling to the right with velocity V, and there's still a magnetic field pointing into the board, and it's the uniform magnetic field covers this entire space, and we'll assume once again the length of the rod is L. So what happens here? Well, there'll certainly be an EMF induced. And now your rod is serving as a source of EMF. And by the way, this is called a slide wire generator. So remember what EMF is? It's that mechanism by which charged particles are taken from lower potential up to higher potential. So I'm pulling on the wire, I'm the person or thing doing the work. Okay, so I'm going to figure out what EMF is induced. In the wire. Okay. And let's go ahead and take a quick look at a simulation of a slide wire generator in action. I pull the rod to the right with speed V. The rod acts as a source of EMF with direction upwards, and hence driving current in a counterclockwise direction. The upward motion of the charges gives rise to a horizontal component of the magnetic force to the left. This is the force I'm counteracting by pulling the rod to the right. Who's doing the work on the system? I'm doing work in the bar, the structure of which transfers this work to the mobile charges. Okay, to figure out what EMF is induced, that is equal to the integral over the dot product of the magnetic force per unit charge and dot dl. So removing this part of the wire here, dl is pointing upwards. And the magnetic force in this case, well, just as before, it's going to have a component that points upward, but there's actually going to be an additional complication from this example over here. In fact, there is going to be a magnetic force to the left as well. Why? Because not only you're pulling the bar, or rod if you prefer, to the right, there's a current flowing, okay? So the magnetic force actually has two components, but as far as this integral is concerned, we're only concerned with that part of the magnetic force that's pointing upwards. So in this case, this just becomes VBL, okay? So when there's a change in flux, magnetic flux, that which happens tends to oppose that change. So another way of looking at this is to see that the area is going to get bigger and bigger. So therefore the magnetic flux through this loop is going to get bigger and bigger. So there'll be an EMF and current induced such to oppose that change, or such as to oppose that change. So in this case, the EMF will be directed in a counterclockwise direction, and hence the current as well. Okay? Okay, so that's the EMF. All right, and as I just said, magnetic fields don't do any work. So who's doing the work? I am. Charges travel to the right with velocity v, but they're also traveling upwards in this segment. And we'll call that velocity u. So therefore, the resultant velocity is equal to u plus v. Okay? Since there are two components of the velocity, we again have magnetic force upwards, but then there's also going to be a magnetic force to the left as well because of this upward motion of charges. So again, applying F is equal to QVB that is going to equal dx in the x direction plus u in the y direction. So that's the resultant velocity. And really, I should write this as w since we have two components here, plus minus bz. So we multiply everything out. I'll have qvb in the y direction, just as before. And then I'll also have minus qub in the x direction. So magnetic force is up and to the left. And it's useful to write this as force per unit charge. Okay? So there's magnetic force due to the left. By me pulling on the rod, I'm counteracting that force. So I pull. Just say me to the right with UVX. Okay? And so as always, it's a good idea to draw a free body diagram. So that's me pulling to the right. And here's the magnetic force directed upwards and to the left. And this makes an angle, we'll call it theta, with respect to the horizontal. And the x component is equal to UB, and the y component has value VB. So I want to figure out, well, what work am I doing on the charges? Oh, that's me. And that'll be equal to UB, distance traveled by the charge, because not only is it going upwards and to the right, or you could look at it another way, not only is it just going rightwards, it's also going upwards. But in any case, the total distance traveled is equal to L over cosine theta. And the angle between these two vectors is just going to be sine theta. So again, good idea to sketch out. We've got our component upwards, velocity component upwards, and velocity component to the right. And the resultant is the sum of those two. And again, U makes an angle of theta with respect to W. So if I look at my little diagram here, U basically times tangent theta is just equal to VBL. Now lo and behold, the amount of work I do per unit charge is exactly equal to the EMF, okay? When I take the EMF, I'm looking at this at an instant in time. Here, in this case, I'm actually following a charge around, okay? Just these are equal to each other. And again, the important thing to note is that it's not the magnetic field that's doing work on the charges. Magnetic field does drive the charge, but I'm the mechanism that does work, okay? Another way of looking at this, if we look at the flux through the loop at some point in time, it's just magnetic field, which is B, and times the area of the loop. So we'll call that L times X. So this is some point in time. Sliding bar is a distance X away from the left-hand side. But we, of course, are interested in the EMF. So that is the derivative of the flux with respect to time, so that's BL dx by dt, which is just BLV, and of course the flux rule tells us EMF is equal to minus the derivative, time derivative of the magnetic flux. But really in this sense, it's easier to keep, forget about the minus sign in the sense that, well, we're going to determine which way it flows using Lenz's law. I think it's a little bit easier to think of that way. So it's BLV, so the EMF is going to be in the counterclockwise direction. And has value magnitude BLV. Okay. Let's take a look at another slide wire generator problem, and this time I'm going to stick a resistor in. Assume that the sliding bar still has length L, there's still a magnetic field directed in the board, and we'll assume at some point in time that the bar is sliding to the right with velocity V. I want to figure out how much power is dissipated in this resistor. Circuits class, that's just equal to I squared, current squared times resistance. And I will use capital cursive R to denote the resistance, so there's no confusion with capital R, which denotes the radius of the sphere, the radius of the cylinder. Okay, so I need to know how much current's flowing. In order to know how much current's flowing, I need to know the EMF. This is basically the same problem, so therefore the EMF here is also equal to BLV. Now the current is equal to the EMF over the resistance. And that's BLV over R. So therefore, the power dissipated, power dis, is equal to B squared L squared V squared over R. Again, where does this power that's being dissipated, it's going to be dissipated in the form of heat. Where does that energy come from? It has to come from somewhere. It's not coming from the magnetic field. Magnetic fields don't do work. I'm pulling on the bar, so I'm the mechanism that's putting energy into the system. It's doing mechanical work on the system. and that energy is going to be dissipated inside the resistor. Now, what happens if I release this bar, it's traveling at some initial velocity v naught? What do you think will happen? Let's take a look at a simulation. Let's suppose I impart to the bar an initial speed v naught and then release it. There will initially be kinetic energy 1/2 mass times speed naught squared. However, once I release the bar, I am no longer doing work on the system, and no more energy will be added. The energy that was initially in the system will be dissipated in the resistor in the form of heat, and the bar will eventually come to a stop. Okay, so the bar has initial velocity v naught. And I release it. I'm no longer doing work on the system. It has an initial amount of kinetic energy. If the mass of the bar is m, the initial kinetic energy in the system is equal to 1/2 mass times v naught squared. Well, I want to figure out what does the motion look like. Well, in any real system, there's friction on these slide wires and it will come to a stop, okay? But only after an infinite amount of time in our model will it come to a stop. Okay, so what happens to, be nice to come up with an equation for the velocity. So how do we do that? Well, force is just mass times acceleration, but that's just the change in velocity with respect to time. And what force is acting on the bar? Well, the current that flows through the bar times L times B. Well, we figured out below what the current is for some velocity V. It's just equal to BLV over the resistance. And therefore, this is equal to B squared L squared V over R. And I'm going to need to erase some of this to give myself a little bit more room. I'm going to solve this for velocity with respect to time. Okay. Collecting all the velocity terms or factors over on the left-hand side, and all the time on the right-hand side, we want it should be a minus sign because this force, magnetic force, is to the left. So that's minus B squared L squared over the resistance times dt. And then I have an m in the denominator as well. Make sure I didn't leave anything out here. No. Okay, so we're good to go. We want to integrate from some initial time, or time zero rather, up to some final time t. And we want to integrate from some initial velocity to some final velocity v. So this will be the natural log of v over v naught. Over the right-hand side, we'll have minus b squared L squared over mass resistance times time. If I take the exponential of both sides, I'll be left with v is equal to v naught e to the minus b squared L squared mass times resistance times time. And there is your expression for how the velocity changes eventually. As t goes to infinity, this will go to 0. Okay? So I'll have a certain amount of initial velocity, 1/2 mass times v naught squared. Infinitely far in the future, all that kinetic energy will have been gone over into the resistor. I will leave it up to you to figure out, or show rather, that the amount of heat energy dissipated in this resistor is equal to the amount of kinetic energy that the bar started with, okay? Okay, so let's look at another kind of generator, an alternator. So let's look at a simulation right now. An alternator is formed of a loop that rotates with angular speed, omega, and a uniform magnetic field. The magnetic flux through the loop continuously changes, and hence so does the EMF. Okay, so our alternator and we've got a loop that's rotating in a magnetic field. The magnetic field is constant, uniform. The flux through that loop is equal to B dot N, where N is the normal to the loop, integrated over some area. Remember, it's always with EMF. It's the change in area that's important. So at any given point in time, the angle between the magnetic field and the normal to the surface of the loop is equal to cosine phi. And if we assume that the loop is rotating with constant speed, angular speed omega, that becomes BA cosine omega t. To figure out the amount of EMF that's induced, that's just minus the time derivative of the magnetic flux, and that's equal to BA. Derivative of this is just minus omega sine omega t. You have minus minuses cancel out, so we wind up magnetic field times area of the loop times angular speed times sine omega t. So that's the EMF induced in the induced in the loop. So remember, generators serve as sources of EMF. Okay. And there's one more problem I want to do that's very much similar to one of the simulations we looked at in Lenz's law. This time I'm going to suppose that I've got a rectangular loop. That'll, for the time being, make calculation a little bit easier. I'll look at it one problem a little bit later on where we've got a straight wire and these circular loops. It takes a little bit more work to get an answer, but for now, we've just got a rectangular loop. We'll assume that it is of height h, and we'll assume that the distance from the wire, the long straight wire, to the left-hand side of the loop is just a s, and then the distance between the long straight wire and the right-hand side is s plus a. So this is a long straight wire that carries steady current. What's the magnetic flux through this loop? Well, it's just surface integral over B dot N. We can use Ampere's law to write down the magnetic field due to the long straight wire. That's just equal to mu naught I over 2 pi s in a circumferential direction. On the right-hand side of the board, the magnetic field is going to be pointing into the board, everywhere over here. So the normal to the loop you can also take as pointing into the board. We'll integrate from 0 to h over dz and integrate over ds, going from s to s plus a, mu naught I over 2 pi s. If I do the math here, I'll wind up with h mu naught I over 2 pi natural log of s plus a over s. Okay, so that's a flux. Well, we're interested in the EMF. When I move the loop up or down with velocity v, there is magnetic flux going through the loop. However, the flux isn't changing because the strength of the magnetic field is the same at all points along here. So magnetic flux stays the same. And hence, no EMF is induced. What about when I pull the wire to the right, or the loop to the right? Well, as you get further and further away, the magnetic field strength decreases as you get further from the wire. Therefore, because nature abhors change, there'll be an EMF induced in this loop, and therefore, let's see, the magnetic field's pointing into the board this way, current's flowing upwards, magnetic field's pointing in here. Magnetic flux decreases as you pull it away, so let's draw a little V to the right in this case. So therefore, the flux is going to be in a direction such as to oppose that change. So therefore, see a current induced in a clockwise direction. So as you are pulling the loop away from the loop itself, you're going to get magnetic field overall magnetic field is not as small as it would have been if the EMF hadn't been induced, okay? So in this case, it'll be flowing in a clockwise direction. To figure out the magnitude, we just want to take the time derivative of the magnetic flux. So we've got mu naught I h over 2 pi, and speed is simply just ds by dt. So therefore, we wind up with 1 over s plus a, we need a minus sign up front here, minus 1 over s times ds by dt, but that's just equal to the velocity. And cleaning this expression up a little bit, I'll wind up with mu naught I h, the height of the loop, a, which is the width of the loop, over 2 pi s plus a, times the speed with which I'm pulling the loop. Now, if I stop dragging the loop along, you just leave it there, the magnetic flux no longer changes. Okay? So this is when I pull the loop to the right.